Hi everyone, this is my video project for my CHEM2523 class, Intro to Organic Chemistry Part 2. So today I'm going to be doing a video tutorial on oxidation and reduction in organic chemistry. So before I get really into the reactions and assigning oxidation states, I think that it's important that you have some sort of understanding as to what an oxidation state actually represents, what this number really means. So an oxidation state, you can think of it's sort of similar to assigning formal charges. It's basically a measure of how many electrons this atom has compared to what it's used to. So we know that carbon, our central atom, is used to having 4 electrons, well, 4 valence electrons, because it's in group 4 of the periodic table. So we also know that when any two unlike atoms are bonded together, the bond is going to be polar in nature because these two atoms have different electronegativities. So for the carbon-hydrogen bond, we know that carbon is more electronegative than hydrogen. So we could say that even though these electrons are being shared, we know that carbon is going to be taking more of them. So you could say that carbon is stealing these electrons, and you can draw an arrow showing that these electrons are going to be directed more towards carbon. And so then you can draw a partially positive charge on hydrogen, a partially negative charge, oh, that's supposed to be a negative sign, not a positive, partially negative charge on carbon. So because that's happening for 2 bonds, and you know that there's 2 electrons being shared in both of those bonds, you could say that from these 2 bonds, carbon is getting 4 electrons. And now when we look at oxygen, we know that of the 2, oxygen is the more electronegative element, so oxygen is going to be taking these 2 bonds worth of electrons, which is 4 bonds. So you could say that from these 2 bonds, oxygen is getting all 4 and carbon is getting 0. So in total, carbon is getting 4 electrons, and it's used to having 4 electrons, so you would say its oxidation state is 0. If carbon were to have more electrons than it's used to, because electrons are negative, it would have a more negative oxidation state. And if carbon were to have less electrons than it's used to, its oxidation state would be positive because electrons are negative, and the atom would be more positive than it's used to. So there are 3 rules for assigning oxidation states that makes it pretty quick to calculate. So for each carbon-hydrogen bond, or carbon-M bond, like a metal, you give carbon a charge of -1 because you know that carbon is the more electronegative atom. It's going to be stealing those 2 electrons, which would be giving it 1 more electron that it's used to, so it would get a charge of -1. For each carbon-carbon bond, carbon's given a charge of 0 because carbon, the bond is nonpolar, the electrons would be shared evenly in between the 2 atoms. You could say each atom is getting 1 electron, which is what carbon would be used to getting from a single bond. And then for each carbon-oxygen bond, or CZ bond, you give carbon a charge of +1 because oxygen is more electronegative of the 2, and it would be stealing that electron from carbon. So M is any element that is more electropositive than carbon, and Z is any element that is more electronegative than carbon. So now we're going to go through a couple examples. So here for our first compound, we have 1, 2, 3, 4 carbon-hydrogen bonds. Right? And you know that from each of those bonds, carbon gets a charge of -1. So in total, the carbon would have an oxidation state of -4. And so for our second compound, we have 1, 2, 3 CH bonds, and from each of those, carbon gets a charge of -1. So from those 3 bonds, carbon has a charge of -3. But we also have 1 CO bond, and you know from that, carbon's getting a charge of +1. So overall, carbon's going to have an oxidation state of -2. And for our last example, carbon has 2 CH bonds, and it has 2 CO bonds. So overall, it's going to have a charge of 0, or an oxidation state of 0. When you have a double bond, each bond counts as its own. You would count each bond separately in a double bond. So this would be 2 bonds having +2. So now here's the overall oxidation state order for carbon. So the lowest possible oxidation state of carbon would be when all 4 of carbon's bonds are attached to hydrogens. So that would give you a charge of -4. And then the second lowest state would be when you have 3 bonds attached to hydrogen and 1 attached to oxygen. So that would be -2. And then following that, you would have 2 hydrogen bonds and 2 oxygen bonds, which would balance each other out. You would have a charge of 0. And then you can have 3 oxygen bonds, 1 hydrogen bond, which would be +2. And then if you had 4 oxygen bonds, like carbon dioxide, you would have a charge of +4. So this is the lowest oxidation state of carbon, and this is the highest oxidation state of carbon possible. All right. So now that we went through how to assign oxidation states, we're going to get into the actual reaction. So reduction of an organic molecule refers to increasing its hydrogen content or decreasing its oxygen content. So reduction is essentially reducing the oxidation state. Oxidation of an organic molecule refers to increasing its oxygen content or decreasing its hydrogen content. So it's increasing the oxidation state. The oxidation state would become more positive. So reduction and oxidation are basically the opposite reaction of one another. So when you're drawing out a reaction, you can symbolize oxidation by square brackets with an O because you're adding oxygen. And you can symbolize reduction by square brackets with an H because you're adding hydrogen. And so you can see that going from left to right, you're oxidizing, and going from right to left, you're reducing. So these reactions are really the opposite of each other. So there are, the reason that we're discussing this, the reason why this is important for this class is because Chapter 12 discusses, what's the title of Chapter 12? Chapter 12 is discussing alcohols formed from carbonyl compounds. A carbonyl compound is a compound with a CO double bond. So we have aldehydes, ketones, carboxylic acids, and esters. And so basically, when you reduce a carbonyl compound, you can form alcohols, which is what this chapter is discussing, which is like the purpose of this chapter. So we can see here that if we're reducing an aldehyde, we can form a primary alcohol. If we're reducing a ketone, we would form a secondary alcohol because we would have the 2 R groups as opposed to just the 1. If we were to reduce a carboxylic acid, we would form a primary alcohol as well as water. And we can see here that the carbonyl oxygen is going to be part of the primary alcohol, and the alcohol, or the hydroxyl oxygen, is going to be part of the water molecule formed. And then for reducing an ester, we can see again that the carbonyl oxygen would be part of this main primary alcohol formed, and then the ester, or ether, I guess, the ether oxygen would be part of this other alcohol that we form. We don't really know what kind of alcohol this is going to be. It depends on the nature of this R group. It could be primary, secondary, tertiary. We're not really sure. So now we're going to go over the reducing agents that we use in this class. So there are 2 reducing agents that we're going to discuss. They are lithium aluminum hydride and sodium borohydride. As you can see, they're pretty similar. The way that the structure is drawn out, they're both pretty much ionic in nature, having the metal with the positive charge and the remainder of the molecule as an anion. So lithium aluminum hydride is LiAlH4, and lithium aluminum hydride is the more reactive of the 2. It reacts very violently with water or any acidic protons, so any ROH, whatever, R can be whatever alkyl chain you have, it doesn't matter, but anything where you have an oxygen-hydrogen bond, it would react very violently with the OH group. And so because of this, it makes this compound a lot more difficult to work with. It requires a protic solvent, and if this were to come into contact with water anytime throughout the reaction, anytime you're working with it in lab, you would get a very violent reaction, and it makes it a lot more difficult to work with. But the advantage to this molecule, to this reducing agent, is that because it's so much more reactive, it has the capability of reducing all carbonyl groups. However, sodium borohydride is less reactive. You can use protic solvents with it. It's a lot easier to work with in lab, so that's advantageous, but it's only capable of reducing the more reactive carbonyl groups, which are ketones and aldehydes, but it's not capable of reducing esters or carboxylic acids, which, depending on what type of reaction you're doing, that may not matter, but that may be important when you're deciding which of the two to use. So now, this is the overall, oh, this is wrong. These are the hardest to reduce, and these are the easiest to reduce. Okay, so we can see that all of these carbonyl compounds can be reduced by lithium aluminum hydride, but only ketones and aldehydes can be reduced by sodium borohydride. And this is the ease of reduction order. Well, I guess the order's going this way. Yeah, this way, sorry, this way. Hardest, going from hardest to easiest, it's going in this direction. So now we're going to draw out the mechanism. I'm getting low on paper. Going to draw out the mechanism for this reaction. We're going to draw out a mechanism using lithium aluminum hydride so that we can get the full, this is the longer of the two mechanisms, and this mechanism contains the sodium borohydride mechanism within it. So I'll point out the two separate mechanisms. So lithium aluminum hydride can be used with esters and carboxylic acids. So we're going to draw the ester reaction. And so when you're drawing out a reaction using a lithium aluminum hydride, you don't actually have to draw out the lithium atom. You would just draw out the remainder of the molecule. All of these hydrogens are very, very negative, and they essentially act like hydride ions. So a hydride ion is H negative. It's a hydrogen with two electrons on it. So the first step in this reaction is you're going to have this very nucleophilic hydrogen is going to come up and attack our electrophilic carbon from the carbonyl group. And so because carbon can only have 4 bonds, then that means that one of these bonds to oxygen is going to have to break, and it's going to come up here to the oxygen. So that is going to form a negative charge on the oxygen, and then our carbon is going to be attached to our group, a hydrogen, and then the ether group. Okay? And so then what's going to happen here is, because the oxygen doesn't want to be negatively charged, one of these electron pairs is going to come back down and reform that double bond, and this electron pair is going to be kicked out because carbon can only have 4 bonds, and this group is going to leave. This is going to act as a leaving group, which will form an aldehyde, and this negative molecule right here. And so then this is the step that is missing from the sodium borohydride reaction, because sodium borohydride can't react with carboxylic acids or esters, so it doesn't have this leaving group step. This is what's different from the two. So then for step 2, once we have our aldehyde, we can react this with lithium aluminum hydride, or we could do sodium borohydride. We'll use a lithium aluminum since we're already using it in the above step. So again, these very electronegative hydrogens, or these very negative hydrogens, these very, what's the word? Anyways, these hydrogens are going to come in and attack this, these electrophilic hydrogens are going to come in and attack the nucleophilic oxygen. Or sorry, these are the nucleophilic, this is the electrophilic one. And then this is going to come up here, and we are going to form a negatively charged oxygen with this compound. So this is almost a primary alcohol. And so now the last step is you would react this as well as this right here with, you would go through what's called an acid workup. And so essentially what you're doing is reacting these two negative molecules with acid, and one of these protons is going to, sorry, that's supposed to be going to the hydrogen. One of these protons is going to be added on to both of these molecules. It would be 2 equivalents of acid for this. And so then you're going to end up with your final product being this primary alcohol and this other alcohol that we don't really know what the nature of it is. It depends on this art group. All right, so this, again, this top step only occurs for lithium aluminum hydride. It would be the same reaction for esters and for carboxylic acids, because the only difference would be this would be an H as opposed to the R prime. And so you would end up with a final product being water. And then this bottom step is for aldehydes and ketones. If a ketone were to be used, the only difference would be that you would have another R group right here, and you would form a secondary alcohol as opposed to a primary alcohol. All right, well, thank you for watching. I hope you learned something throughout my video. If you have any questions, leave them in the comments, or I know I have messy handwriting. If there's anything you couldn't quite make out, please let me know, and I will try and clarify that. Thank you.